Hello, my dear students. Welcome to my YouTube channel, That's Concepts of Chemistry. Before starting today's lecture, please do subscribe this channel and press the bell icon to get the regular updates of the upcoming lectures. My dear students, in the previous lecture, we have done about the molecular orbitals. There I have told you that molecular orbitals is of two types. The one is the bonding molecular orbital and another one is the anti-bonding molecular orbital. In today's lecture, we will study about the energy orders of that molecular orbital, and we will also learn to fill the electrons in that molecular orbitals with specific set of rules with the help of an example, that's O2. O2 example was taken in the previous lecture also. And after that, we will study about the bond order. Bond order is a concept of certain formula by which we get the number of bonds between the two atoms. So now let's move to the screen. So now I'm going to make the molecular orbital diagrams for O2 molecule. So now my example is O2 molecule. What's the atomic number of oxygen? It's 8. So what will be its electronic configuration, my dears? It comes out to be 1s2, 2s2 and 2p4. So now I am making the orbital diagram for first of all oxygen atoms, and after that I will make for the O2 molecule. So I am taking my first oxygen atom on left hand side and second oxygen atom on the right hand side. That's the 1s of first oxygen atom. That's the 2s of first oxygen atom. And that's my 2p of first oxygen atom. Now let's move to the second oxygen atom. That's the 1s of second oxygen. That's the 2s of second oxygen atom. And that's the 2p of second oxygen atom. Now 1s of first oxygen will intermix with the 1s of second oxygen to give you two set of orbitals. One is the bonding and another one is the anti-bonding. So I got the first of all bonding molecular orbital for the 1s, and 1s and 1s overlap to form the sigma bond. That's why it will be called as sigma 1s. Now another molecular orbital is anti-bonding molecular orbital from intermixing of 1s of first oxygen and the 1s of second oxygen. Now it's an anti-bonding, so it will be called as sigma star 1s. Now let's move to the 2s now. The 2s of first oxygen will intermix with the 2s of second oxygen, and we got bonding molecular orbital, that's sigma 2s. Now again 2s of first oxygen will intermix with the 2s of second oxygen, thereby we get the anti-bonding sigma star 2s. Now let's move to the 2p. Here we will get first bonding molecular orbital forming the sigma bonds, so it will be sigma 2pz. Then we will get bonding molecular orbital forming pi bond, that's pi 2px and pi 2py. Then we will get the anti-bonding molecular orbitals forming pi bonds, and they will be named as pi star 2px and pi star 2p y, and finally we will get the antibonding molecular orbital of 2p and 2p forming sigma bond, and that's sigma star 2p z. So this is the molecular orbital diagram up to 2p. Now on left and the right side we are having atomic orbitals. That's the atomic orbitals of first oxygen. That's the atomic orbitals of second oxygen. In center we are having molecular orbitals of O2 molecule. So in the center we are having molecular orbitals, and these molecular orbitals are arranged according to their energy orders. The sigma 1s is at the lowest point, so it will be have the lowest energy. Sigma star 2pz is at the highest point, so it will have the highest energy. So I am writing the energy order for these molecular orbitals now. The lowest energy is of sigma 1s, then there will be increase of energy, and now it is sigma star 1s. Now there is a turn of sigma 2s. Now there's the turn of sigma star 2s. After that sigma 2p z. After that pi 2p x, pi 2p y. After that pi star 2p x, pi star 2p y, and finally the highest energy is of sigma star 2p z. So this is the energy order, and it is the pattern of increasing energy. Increasing energy. So we got the energy orders of the molecular orbitals now. Now I am going to fill the electrons in the molecular orbitals with the help of atomic orbitals. So let's fill them. First of all, the electronic configuration for oxygen atom is 1s2, 2s2 and 2p4. The same goes to the second oxygen, 1s2, 2s2 and 2p4. Now we are having in total of 8 electrons with the first oxygen and 8 electrons with the second oxygen. That means we have to fill total of 16 electrons in molecular orbitals of O2 molecule according to the energy order of the molecular orbitals. That means we have to fill the 16 electrons in the molecular orbitals. So now I am filling them. First electron in sigma 1s, second electron in sigma 1s. Then electron will be filled in the next higher energy molecular orbital, that's sigma star 1s. So the third electron over here, fourth over here. Then is the turn of sigma 2s, fifth electron, sixth electron. Then is the turn of sigma star 2s, seventh electron, eighth electron. After that sigma 2pz, ninth electron, 10th electron. Now pi 2px and the pi 2py, 11th, 12th. Here we have to follow the Hund's rule. Then pairing 13th, 14th. Now this is the turn of pi star 2px and pi star 2py. We are having two molecular orbitals together. They are degenerate, so we have to follow the Hund's rule. So the 14th electron sorry, 15th electron and the 16th electron. So we got total of 16 electrons in the molecular orbitals of O2 molecule. Here you can easily see that pi star 2px and pi star 2py are having two unpaired electrons. That's the reason O2 molecule is paramagnetic in nature. Whenever any atom or any molecule will have unpaired electrons in their atomic orbitals or molecular orbitals, then that atom or a molecule will be paramagnetic in nature. That means it will be attracted by magnetic field. If all the electrons are paired up, then that is a diamagnetic substance and will not attracted by the magnetic field. In case of O2, I have told you in the previous lecture, the Lewis symbols tells us that all the 16 electrons are paired up, so O2 molecule must be diamagnetic. But we found it to be paramagnetic experimentally. From there, we got the new concept called molecular orbital theory. And in the molecular orbitals, you can easily see that in O2 molecule, there are two unpaired electrons in pi star 2px and pi star 2py. That's why O2 molecule is paramagnetic in nature. So I'm writing because of the presence of because of the presence of two unpaired electrons, comma, O2 molecule is paramagnetic in nature. That means O2 is getting attracted towards the magnetic field. So now I am writing about the molecular orbital electronic configuration of the O2 molecule. Now I am taking the topic to be molecular orbital electronic configuration of O2 molecule. So I am writing its configuration is, first of all, sigma 1s is having 2 electrons, then sigma star 1s is having 2 electrons, then sigma 2s is having 2 electrons, then sigma star 2s is having 2 electrons, then sigma 2p z is having 2 electrons, then pi 2px, pi 2py are having 2 electrons, and after that we are having 2 unpaired electrons in pi star 2px and pi star 2py, that is 1 electron and 1 electron. So this is the molecular orbital configuration of O2 molecule. Now let's move to the bond order now. Bond order. What is bond order in a simple terms? It is the number of bonds between two combining atoms. What's it formula? The formula for bond order is number of bonding electrons minus number of anti-bonding electrons divided by 2. In a simple terms, we can write that bond order is equal to the number of bonding electrons minus number of anti-bonding electrons divided by 2. Now let's evaluate the bond order for O2 molecule. I am writing O2 molecule now, and I am calculating its bond order. It is equal to, first of all, number of bonding electrons, and we have to count the number of anti-bonding electrons in O2 molecule. Now, here the bonding electrons are those in which we are not having stars. That's the bonding molecular orbital. That's again the bonding molecular orbital. So these will be the bonding electrons. That's again the bonding molecular orbital. And that's again the bonding molecular orbital. So I have marked the bonding molecular orbitals. Now let's count the number of electrons that are present in bonding molecular orbitals. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 and the 10. We got bonding electrons to be 10 in number. Now let's count the number of anti-bonding electrons. Here, anti-bonding molecular orbitals are those on which I have marked the star. And we have to first of all identify the anti-bonding molecular orbitals, and after it we have to count its electrons. So this sigma star 1s is anti-bonding molecular orbital. This sigma star 2s, this sigma star 2s is anti-bonding molecular orbital, and this pi star 2px and pi star 2py is anti-bonding molecular orbital. So now let's count the number of electrons over there. The first electron, second electron, third electron, fourth electron, fifth electron and the sixth electron. We got the 6 electrons in anti-bonding molecular orbitals. So we got 6 electrons in anti-bonding molecular orbitals. Now I am putting these values in the formula. Bonding electrons are 10 in number. Anti-bonding electrons are 6 in number, divided by 2. I got my bond order to be 10 minus 6, 4 upon 2. It comes out to be 2. So the bond order for O2 molecule is 2, and it signifies that 2 oxygen atoms will have 2 bonds in between them. So that's all about bond order. So now, what are the different properties that depends on the bond order? I am writing, if bond order is high, that means we are having more number of bonds between two atoms, then bond dissociation energy will be high. That means very high energy is required to break that more number of bonds between two oxygen atoms. Or we can say bond stability is high, or you can also say bond strength is high, and if bond strength is high, bond stability is high, bond dissociation energy is high, we are having more number of bonds, so that's why higher bond order, due to which what's going to happen, bond length will be low, bond length will be low. That means if there are more number of bonds between combining atoms, then that more number of bonds will pull that two atoms closer to each other. That's why their bond length will decrease. So their bond stability is high, bond strength is high, bond length will be low with the higher bond order. So that's all about the molecular orbitals. That's all for today. I hope you all understood the energy order of the molecular orbitals, the rules to fill the electrons in that molecular orbital, to specify whether the molecule is paramagnetic or diamagnetic, and also the bond order. So, if any student wants to book a paid one-to-one online class to clear their doubts, then he she can contact me. My phone number is mentioned on the thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.